In this segment, I want to talk about how polymorphism arises in practice. That is, how do polymorphic functions come to be polymorphic? What I want to do is take a look at some examples and we'll see how that happens. I guess the crucial principle is that polymorphic definitions arise because there's nothing to constrain the types to be any more specific. And let me just run through a few examples of that. Now, let's take the definition ID of x equals x. What do we know about the type of this? Well, we know the type of the input and the type of the output are the same. It takes an x in and it outputs an x. But do we know anything else about that input at all? Answer is we don't. So the type of this is going to be A arrow A. It will simply take something of any old type to that same old type. So that's our first example. Let's take a second example. Here we have a function that takes a pair of things, x and y, and returns the first element of that pair. So we know here that the x in the input and the x in the output are of the same type. And we also know that the input is a pair. So the type is going to look something like this. It takes an input of a pair as input, and it returns an output. And the thing in the first place of the input can be of any type, and that type's the same as the result. Now what about the y? The y is completely unconstrained. Y could be any type, whatever. It doesn't have to be the same type as x. So what we do is we give that another variable so that a and b are arbitrary and different, so that instances of this might be int, comma, int, arrow, int, but they could also be something like int, comma, char, arrow, int. Okay, that's our second example. Our third example is a bit more complicated. It's this: lengths of x's is length of x where x comes from x's. So what do we know here? What can we tell from this definition? Well, in here we're applying the length function to this input, this value x. So this value x must be a list. Let's say it's a list of A. We don't know anything more about its type. Now x has come from that input list x's, so that must be of type list of A. Because we're applying this to a list of lists, and each of the lists inside has its length taken. So what we will do is we'll take a list of an arbitrary type, and we will return a list of int. Because for each list of type A, when we apply length, we get an int. As we're taking a list of these lists, we get a list of integers as the result. Just to confirm what I've shown you, we get ID is of type A arrow A, completely unconstrained. First takes a pair of things and returns something of returns the first component, so the type of that and the type of the first component must be the same. And lengths applies the length function to every element in a list. So we take a list of lists and we return a list of integers. And that's how polymorphism arises. So we'll go back to this in more detail later in the course, but for the moment, the crucial message is the one that you see here. A definition is going to be as polymorphic as it possibly can be, because there's no reason for it not to be in those particular examples. Now, polymorphism is crucially, these are generic or polymorphic functions, so there is one definition for all types. So for example, here's a very simple definition. It takes an arbitrary item and gives you back a list of those items where you've duplicated the value. And so that takes something of type A, that might be an int or a bool, and returns a list of A. But that same definition applies at all types. That's entirely different from overloading. So overloaded functions, we've talked a bit about these as instances of type classes. What type classes allow us to do is use the same symbol, like equals equals, at different types, denoting different functions. So the function, for example, I've just shown here the functions for equality over booleans. So true equals true evaluates to true, false equals false evaluates to true, and any other combination of true and false evaluates to false. So equality over booleans is defined by pattern matching, essentially. What about equality over pairs? Well, you define the equality over pairs using the equality for the first type, x equals w, and equality for the second type, y equals z. So those two definitions are entirely different. Different definitions are used at different types, and the class mechanism allows that to operate properly. It resolves which of those equality functions to use depending on the type where it's being used. Whereas polymorphism, genericity is a lot easier because you use the same definition at every type. I just wanted to say one more thing about lists and types before we move on. Now, there are other types in Haskell that you could call listy, or the technical term is foldable. So there are other types that you can treat as if they were lists, or behave like lists in some ways. And so just like we have a whole lot of classes of numbers, Haskell has a whole lot of types which are instances of the foldable type class. It's modeled on lists, but there are other types inhabit that type class. I'm not going to talk about this until right at the end of the course, but the reason you come up against it is because if you ask GHC for the type of length, it will say, oh, it's foldable T, fat arrow, T arrow int, which is telling you something about the type class mechanism. What I would recommend you do in those situations, ignore the foldable T part and replace the TA by list of A, and you will see this is a correct type for length. It's not the most general type, but it's a correct type. So anytime you see an instance with foldable T, you replace every T of A by list of A and ignore the bit before the fat arrow. And that gives you the list type of the function specifically, rather than all the listy types that you get by making it foldable. Okay, let's move on to actually talk about some real functions over lists now.